Okay, you're welcome to today's presentation. My name is Jefta Oimai, and I'll be taking us through a project that I titled Design and Control of a DC Hybrid System for an Off-Grid Based Transceiver Station in Nigeria. The course instructor is Professor Moshe Jamil. So in developing and underdeveloped countries today, energy has remained a very significant challenge. While the mobile communication industry continues to grow at a tremendous rate. With this growth, more base station sites are required. Some of in remote location without electricity. So the need of energy in rural and remote areas where conventional power supplies are available has resulted in deploying distributed energy, renewable energy to these areas to help provide this power to their immediate needs. So the objective of this project is to design and control a hybrid energy system for a base transceiver station in a location in Nigeria, which you can see Oron, Akwa Ibom State. This location is an interior and a remote area where grid system or grid power is not channeled there. So they are always faced with power instability and technical issues relating to power. So the significance of this project, a lot of research has been carried out on the economics of using the hybrid system instead of the conventional one, which is a grid, as we know. But little is done about simulation, about the control of the system, about the working together of the various renewable sources. So little has been done about that. So this project aims and is prepared to tackle that issue in a very, explicit manner. So many researches have been done. Many research has been done regarding, the hybrid configuration, and as we have said in the previous slide, little is being done in the aspect of control and management of what the synchronization of these various hybrid systems. So researchers have extensively investigated renewable sources for base transceiver stations, standalone application, and hybrid application. This research has been championed by academicians, and industry experts who strive to reduce the carbon footprint of communication network every day. So one of the researchers which I've looked at in this project is Kitindi, proposed a hybrid off-grid power system for a remote mobile base station in Morogoro, Tanzania. So this system was modeled and simulated, to get the techno-economical analysis and the feasibility study using OMA software. Another researcher is TRANSCEIVER, conducted a feasibility study of the hybrid PV system to provide power for low load profile. So system definition. So like I said, in a broader sense, as you can see in different pictures, shown in the screen, we have the BTS, the base transceiver station. This is can be likened to the 3G or the 2G system. So this is a system that would need to power, and it's located in Oron. You can see the longitude and latitude. It was taken in Oron. Then is the load profile. Using a DC monitoring system, MTM, we got the load profile for that particular site. Now this is the site. This is the landscape, the picture of the site with just a generator. So this project, as I've earlier said, would help synchronize various renewable sources and get the most effective and the techno-economical configuration for a better efficiency and better output production. So the hybrid configuration. So in the hybrid configuration, you can see we actually make use of OMA software, and this system I streamline my equipment to the DC mode. DC mode being that the conversion process losses are involved. So with the DC mode output, losses will be reduced minimally. So you can see the generator, the DC generator connected to the DC bus bar. You can see the wind. Like I said, we're having a synchronization of various renewable sources. Then afterwards, later slides, we'll talk about the most cost-effective one. So you can also see the load. You can see the battery as connected to the DC bus bar. So you can see from this the specifications of the components we are using for this design. We are using the solar photovoltaic, and with a cost of $1,000, over a lifetime of 25 years, which is a very good one. You can see the backup battery, cost of $400. 97% efficiency, very beautiful. You can see the 6,800 cost. You can see it's over 25 years. So these are the setup and the configuration components that will be used in the design. So after employing OMA in our configuration, synchronization, choice or synchronization measures, we discover that the PV DC battery had cost of energy to be $0.22. We can see the PV wind diesel battery had cost of energy to be 0.256. You can see PV diesel, which is a photovoltaic and a diesel. You can see it's 0.329. You can also see diesel alone 0.340. So with this OMA software, I've streamlined my options to using the PV, diesel, and battery setup for my design, because over years it has a cost of energy to be 0.223. So this, of course, would save cost over a very long time. So the dynamic model. So in dynamic model, we're talking about the control of this setup, because like I said, little has been done about the control of the setup. So considering the control of the setup, will be modeling the solar photovoltaic system, hybridizing it with the battery storage system, and the diesel generator for a better waveform and a better output signal, which we'll be looking at using the MATLAB Simulink at later slides. So with the solar photovoltaic system, you can see the circuit diagram with the input current source, and you can see two diodes. And with the diodes, you see that the diodes provide a low resistance, path, for current flow. So you can see the resistor load, which is a load at the end of the day. Then you can see the battery storage system. Then the buck converter. So the buck converter will be, used in this design, because it helps to to step up the current. And then of course we have other voltage regulator, voltage converters, So it's just like the voltage divider. We have the Zener diode, and but this voltage, converters, they have, the heat, they dissipate heat, as power. So that reduces, the efficiency at the end of the day. So now I'll be making use of a buck converter, because with buck converter, dissipation of heat is minimal, and a lot of stepping up of current will be involved using this. So you can see the DC voltage source, you can see the MOSFET, which is a switch, you can see the diode, the one directional pathway for minimal, flow of current. You can see the RL circuit, you can see the capacitor. The capacitor is just, to maintain a relatively stable output voltage across the load. So the supervisory control strategy. Supervisory control strategy is one of the the control strategy we're going to be be employing in this design. So first we'll be using the battery charge controller. So the battery charge controller is just a controller that would have a reference voltage, 48 volts. Of course, telecoms, the big use of 48 volts. So have a reference voltage and have it's monitored to give a signal at the end of the day. You can see this is the circuit representation using MATLAB software. So another supervisory control strategy I employed in this project is the maximum power point tracking, the MPPT. So this is just to track the sun for better output production for the solar system. And you can see the solar has the solar arrays. As the sun comes, we have the solar arrays. Now with if it's a direct impact, without a fractional pull out from the solar arrays, you have a direct flow to the DC-DC converter. But with the slight deviation, you have the MPPT control algorithm tracking the sun and sending the power to the DC-DC converter, and that is sent to the DC load or sent to the battery or the inverter, as the case may be. But here we'll be making use of the battery and DC load here. So this is the general setup of the MATLAB Simulink system modeling. Now with this, you can see from the from my left hand side, you can see the solar setup, the solar system with the irradiance. With the irradiance, we have to selected irradiation for this region. Then the temperature, which is around 35 degrees centigrade, was selected, and you can see the output, what do you call it? The output voltage and current was measured. You can see, and we can see the buck converter. The buck converter just between the load and the solar. You can see the buck converter circuit trying to convert the circuit and regulate this output from the solar system. Then we can see the diesel generator. The diesel generator, just like a standby system, just when at times when the sun is out and it comes in for just like a standby system. Then we have the battery. The battery, which will be our storage system, is just at the restroom, right? Then the charge controller. The charge controller, so I've discussed in the previous slide, the charge controller just controls the charge. When the battery is low, it's picks up it sends has the interference with the reference 48 volts, and the control through the PID controller is implemented. Now we have the MPPT controller. The MPPT controller, as we said, is just the tracking of the sun. So with this, we can be able to have a better output, a better efficiency from the solar system. So the simulation results, these are the graph outlined here. The simulation results from the simulation from the MATLAB Simulink. You can see the solar irradiance. The solar irradiance at the maximum of 1000 irradiation. You can see the output power from the PV. Output power from the PV, because the highest the higher the irradiation, the higher the power. Yes, you can see the state of charge. The state of charge just like in a shape form. You can see the steady, DC voltage, standing at 50 volts. Simulation result continues. We have the PV output voltage, PV output current. You can also see it here. So just few of the simulation results. You can also see the load current standing was a DC load, and it's going to be uniform. So we can see the load power just at 4,000. Below 4,000, which is 3.2, because with it's 3.2. So conclusion. So with all this, we've been able to get a sustainable solution. With this sustainable solution, this community or local government in Nigeria will be able to get a reliable source, with tracking of the sun, monitoring of the battery. We tend not to have bad batteries. We tend to trap a lot of power from the sun, and at the end of the day, we are managing our equipment. Our equipment are running at the highest efficiency, and the production of electricity for this standalone base transmission station, which is the BTS site, is achieved. We can also see low carbon emission. So employing these renewable sources, we can have a low carbon emission. Of course, the generator will just come in, occasionally to just back up when the sun is out. So higher reliability with the control, reliability will be at the very high level. So energy security. Because of employing these various configurations and synchronizing them, I believe at the end of the day there will be a more reliable and energy more secured energy for this base transceiver station. So with this, these are a few of the references we made use of in this project. Feel free to go through them and for better understanding and better concurrency with the project, as the case may be. So thank you. I appreciate you for your time. It's been a pleasure running you through this project, and I hope to have more future works done on this project, better simulations and better results for a better engineering experience. I really appreciate you and look forward to doing more projects in the future. Thank you.